Hi, I'm Mike Bunds from Utah Valley University.
Hi, I'm Chelsea Scott from Arizona State University. And today we are excited to tell you about how we recently collected 40 kilometers of high-resolution topography along the Southern San Andreas Fault from Painted Canyon to Bombay Beach.
To collect this data set, we used a small uncrewed aerial system and structure for motion processing and produced a well-georeferenced 10-centimeter DEM and associated orthoimagery in only about 3.5 days of fieldwork. The data set will soon be publicly available on Open Topography.
So here is a map of Southern California. This is Palm Springs, where SCEC is normally located. Here is the Southern San Andreas Fault. This is Painted Canyon, a well-known structural geology site, and Bombay Beach. And we collected the high-resolution topography from just north of Painted Canyon, 40 kilometers south to Bombay Beach. There are several motivations for collecting this data set. First, we wanted to collect a data set along the well-studied Southern San Andreas Fault that would become publicly available, could be used in a variety of geology and geomorphic studies. We also wanted to refine a methodology where we could collect high-resolution topography that is well georeferenced after an earthquake in response to, for example, a future earthquake along the Southern San Andreas Fault. And finally, we wanted to collect a good pre-event data set for differencing to be used following a potential subsequent earthquake along the Southern San Andreas Fault.
To collect this new data set, we conducted field work in February of this year, 2020, over about 3.5 days. We had a crew of 4 people, although this work could easily be done with 2 trained people, potentially 1 for parts of it. We used a SenseFly EB+, which is a fixed-wing, small uncrewed aerial system that has onboard multi-frequency differential GNSS capabilities. Each day, we established a geodetic quality local reference station, and data from that reference station was differenced against the data from the onboard system on the UAS to generate PPK solutions for the camera positions. We also measured checkpoints for quality control, 175 checkpoints in total, 24 of which had a target similar to what's normally used for a ground control point, which allows a horizontal error assessment. To process the data set, we did draft processing each night on GPU-equipped laptops. And then in the office, we did PPK differential solutions for every camera position against our reference stations. The reference station positions were solved for using the OPUS system and precise ephemerae. The structure for motion processing was done on AgiSoft Metashape, where we ran the project as a single chunk on a cluster of 5 workstations, which was able to do the computer processing in about 48 hours total time for the camera alignments and the dense cloud production. And the model was georeferenced with about 15,000 PPK solutions for the camera positions. The final data set covers about 30 square kilometers of area and consists of about 8 billion points in the point cloud. Uncertainty in the data set, which is measured relative to the reference stations using our 175 checkpoints, is a vertical RMS error of about 4.5 centimeters and a horizontal RMS error of about 2.3 centimeters.
One of the applications of our new data set is to perform topographic differencing. Here's an example of differencing our 2020 small UAV data set. So here is the topographic hillshade near Painted Canyon. And this is the vertical difference between the 2020 data set and the 2005 before data set. Here is a second example. This is showing the Coachella Canal. We'd like to acknowledge funding for our project, including funding from SCEC awarded to Scott and funding from the UVU Office of Engaged Learning and College of Science that was awarded to Bunds. So thank you, and we look forward to seeing you at SCEC.